Okay, this video is for Module 6. This is commonly missed problems from Exam 4 that you're going to see in this module. So let's take a look at a couple concepts, path versus circuit and Euler versus Hamilton. So a path is any series of connecting edges. So really one edge is a path. Now if you do 2, that's also a path. Okay, so we start here, we go up, that's a path. However, a circuit is going to come all the way back to where you started, so it begins and ends at the same vertex. So if you start here, it goes up, right, down, and back, and we're back to where we started. That is a circuit. Now, in Euler versus Hamilton, Euler is concerned about passing through every edge, and Hamilton's concerned about passing through every vertex. And so, an example of an Euler path and an Euler circuit, well, we just seen this one here. We went through every edge, and that's an Euler path. And of course, since we started where we ended where we started, that's also a circuit. So this one here is actually a path and a circuit. Okay? A circuit is just a specific type of path. Now, for Hamilton, we want to pass through every vertex. We do not have to pass through every edge. So if we start here, we go up to the right, down, and to the middle, and we've hit every of the 5 vertices here. That is a path. A circuit, we have to end where we started, so we're going to go up, right, down, middle, and then back to where we started. And that would be the Hamilton circuit. Okay, so let's talk about determining a path that includes all the edges without using any edge twice. So that is basically asking for an Euler path. So we have a little bit of guidance from Euler's theorem, and basically we want to focus on the vertices. So Euler's theorem talks about having, if it had no odd vertices, then it has at least one unit Euler path and an Euler circuit. If it has exactly 2, then it talks about having one Euler path but no Euler circuits. And a graph with more than 2 odd vertices has neither of those. So if you see more than 2 odd, you're going to have to say there is no path. So if we take a look, this is that's 2 degree of 2. There's 2 edges coming from that vertice. There's 3 edges here. There's 2 here. There's 2 here, and there is 3 there. So this does have 2 odd. So because it has 2 odd, it says each Euler path must begin and end at one of the 2. So basically, we can pick either C or D, and I'm going to pick D. And we can just do D to F to E to C to D to B to A and then to C. So basically that did D, F, E, C, back to D, up to B, left to A, and then down to C. And there we've covered all the edges. Okay, so this is just one example. There are many other different paths you can make. That's just one example. Okay, let's talk about finding a route that crosses each common state border. And when we talk about crossing, that is crossing a path, making Euler paths. So we can use Euler's theorem for this down here at the bottom. And so what you could do, you can connect them here as they are, or you can make your own graph on the right. So Washington, Montana, Oregon, Wyoming, and Idaho. and notice that Washington and Montana, you can't connect them. You have to go through Idaho. Okay, you can't cross like this, and neither can Oregon cross into Wyoming directly. You have to go through Idaho first. So we want to go through every graph. And how do you know where to start? Well, we have to use Euler's theorem to figure this out. And to use it, you got to know all the degrees of the vertices here. So just looking at the number of edges that connect, there's 2 here, 2 here, 2 here, 2 here. And in the middle, we have 4 edges that connect. So all of these vertices are even. So that means we can look at Euler's theorem number 1. There's no odd vertices, which means there is a path, there is also a circuit, and you can be started at any vertex. So we're free to start wherever. So we can, just as an example, we can start in Idaho and then go to Montana and then do Wyoming and then Idaho again and then Washington and then Oregon and then Idaho. So that, what I just did was I went up here, went down, came back, kept going this way, went down, and then back to Idaho. All right, now let's take a look at finding 2 Hamilton paths. Remember that Hamilton is concerned about passing through every vertex, not necessarily every edge. So we can start at B, and we can go to A, then we can go to E, and then F, G, H, D, and C. Okay, we're not going to go down to G because we have already passed through G. We've already visited that spot, so we're not going to do that again. You can only do it once in a path. For the circuit, you'll be able to come back to where you came from, but that's the only one you can repeat. So we are done. So let me go ahead and write down the path here. So B, A, E, F, G, H, D, and C. And notice that each letter is only used once. Okay, so to find a different path, let's say we started at H, and we go up to D, to C, to G, to F, to B, to A, and then to E. And that would be another example. So we started at H, went to D, C, G, F, B, A, and then E. And there you have it. What about finding the minimum cost spanning tree for the graph? Well, you want to go ahead and find the smallest numbers first. In this case, I see some single digits, so we're definitely going to use this 1, this 3, and this 6. So that creates like a Y right there. And now we need to get to H. So the question is, what's the cheapest way to get to H? And that's going to be not the 49, but the 14. So this is too expensive to get to H. And then how do we get to D? Well, let's see this F. We have 21, 27, and 31. So these are the 3 ways to get to F, and I'm going to choose the cheapest way, which is the 21. And so what about getting to the other side, to the right? And we need to choose between 31 and 36, and we're going to choose the 31. And now 15 is a really small number in this area. So that's basically our tree. If you wanted to see it separate, looks like this. And then how would you add this all up?